Good morning, dear listeners. My name is Alexey Maslov. I'm a young researcher with Utah State Aviation Technical University. Today I want to tell you our results in deposition of max phases coatings by cathodic arc deposition without any substrate heating, just using hollow cathode plasma source assistance. Next slide, please.
Кликер у вас? Нет, кликер там лежит.
Thank you. But first of all, let me to say you what max phases are. This is a new group of ternary hexagonal carbides and nitrides with a similar cell structure and similar stoichiometry. It's M n plus 1 AXN, where M means a transitional metal, A is an element of 13-14 groups in periodical system, or 7A in American interpretation, and X is a carbon or nitrogen. This group of compounds is relatively young and it's far from being fully investigated. Here we can see the typical structure of cell unit of these phases. They have 2-1-1 structure, 3-2, and 4-1-3. Properties of max phases is quite interesting. They have a unique combination of properties, physical and mechanical. As their discoverers say, they bridge the gap between metals and ceramics. Some of max phase systems, for example titanium aluminum carbon, demonstrates promising high temperature capability in bulk form, and this allows us to suppose that these phases is quite effective as a oxidation resistant thin films. Here you can see on the picture, you can see a mechanism of oxidation of titanium to aluminum carbon max phase. You can see a critical temperature is 1400 Celsius degree. It's quite not bad temperature, no. But thin film deposition of max phases is quite challenging. Today we know about three main problems. It is mismatch between target composition and thin film composition if we talk about compound sputtering, max phase target sputtering. This is a thin film resputtering by heavy ions and atoms, especially if we talk about systems with really different elements. For example, tantalum and aluminum carbon. And the third problem is an element evaporation due to high substrate temperature which is needed to provide synthesis of max phases. It's typically more than 700 Celsius degree, which is far above than most A elements melting point. The main goals of my work. The first is to try to deposit titanium to aluminum carbon max phase using two compound targets, titanium and aluminum, without any substrate heating and using hollow cathode plasma source. The second is synthesis titanium to aluminum carbon max phase with hollow cathode plasma source by titanium aluminum cementation. It's quite low, excuse me. And the third, in the future, is to synthesis max phase by max phase target sputtering. But we don't have max phase target yet. Our experimental procedure. On the left picture you can see our vacuum chamber equipped with two arc evaporators, 1 and 2, titanium and aluminum respectively, and the hollow cathode plasma source which assist in the deposition process. On the right picture you can see a principal scheme of this. We obtained this from Tomsk, thanks to them. The first one is a hollow cathode. The second one is arc igniter, the third is magnetic coil, the fourth is arc suppressor, the fifth is isolator, and the second and sixth is isolator, and 7 is vacuum chamber. The plasma comes along the axis into the vacuum chamber. This is scientific equipment which we used. This is a scanning electron microscope, the scientific Swiss knife, you know, and the right picture you can see X-ray diffractometer. This is a visual examination of samples after deposition. On the left picture you can see as deposited. sample. In the middle you can see unusual yellow annealed sample, and there on the right picture you can see a sample after cementation. Let's take a look on the X-ray analysis. This is the X-ray pattern of sample without annealing. As you can see, there's no any signal of max phases or even titanium carbides. You can see titanium peaks, alpha titanium peaks and beta titanium peaks. Our substrate was a Ti2AlC alloy. It is just technically pure titanium, and its peak is shown here. But situation changed dramatically when we use annealing. You can see much more crystallinity, and you can see blue peaks of our desired max phases, as well as some titanium carbon peak. But what most interesting of this picture is the biggest peak with excellent matching. It's about 95%. It's a titanium, aluminum, carbon, nitrogen. It's a max phase carbon nitride. It was quite surprising for us because design of experiment did not involve nitrogen. So one explanation that I can provide you is that vacuum furnace used for annealing was not vacuum enough. But we will examine it later. Here you can see a quantitative analysis. Please keep it in mind that our X-ray diffractometer rays penetration is compared with thin film thickness. It's about 20 micrometers. So you can see a large amount of substrate material. And if there was no this anomalous carbon nitride, the max phase content will be significantly higher. This is scanning electron microscopy. As you can see, our thin films have a good microstructure with low porosity and some molten drops. This is a drawback of cathodic arc deposition. Here we can see X-ray pattern after cementation. Unfortunately, I must say that cementation is probably not the best choice to synthesize max phases. You can see no peaks of any carbides or max phases, just titanium and titanium aluminum intermetallics. And little bit conclusion remarks. First of all, I should say that we will investigate our carbon nitride more deeply to understand its formation mechanism, because in previous work there was needed a high pressure and high temperature to synthesize this carbon nitride, and we did not apply any pressure, so it's looked quite curious. Max phase formation by cementation is not confirmed as we expected, and we think that in general, if we will perform more correct deposition and annealing, this technology is viable for synthesis max phases in reasonable amounts. Thank you all very much.